If you've ever flown on a commercial flight or been in an airport, chances are that you've seen a winglet or two of some kind before. Winglets are a classic approach to decreasing the drag on and increasing the overall efficiency for a given aircraft. So what do these things do? The primary intention of a winglet is to improve the aircraft performance by decreasing the induced drag generated by a lifting wing, thus increasing the overall efficiency of the aircraft and decreasing the fuel or energy consumption. If you're not familiar with what induced drag is and why there are different types of drag, let me fill you in real quick. As a refresher to the absolute basics of aviation and aerodynamics, there are two major contributors to the total drag of an aircraft, and these are profile drag and induced drag. This bar graph shows a typical cruise drag breakdown, and you can see that the skin friction, profile drag, and induced drag account for like 80% of the total drag, so it's really only natural to try to decrease one of these before chasing down the others. Plus, you'll see that it's much more challenging to meaningfully decrease the secondary contributors to the total cruise drag here. Profile drag refers to the sum of all drag forces acting on an airfoil that are not related to the generation of lift. This would include both skin friction and the pressure or form drag. A simple way to understand profile drag is that it's the measure of the consequences of viscosity added to the pressure drag of an airfoil. The pressure drag is a result of the pressure forces acting over the front side of a lifting body not being longitudinally balanced by those pressure forces acting over its rear side. The explain it to me like I'm five explanation of this form of drag is that as an object moves through a fluid, it will effectively pull some of the fluid along with it as a result of viscosity, and this leaves some of the fluid in motion. Now, this energy to put it into motion had to come from somewhere, so the energy transfer is exactly what we refer to as profile drag. Profile drag is mainly dependent on airfoil shape, wetted area, and the angle of attack, and just like lift, profile drag is proportional to the square of the velocity. The other important form of aerodynamic drag is called induced drag. This is the consequence of producing lift in a finite span wing and is basically just the result of the lift generating pressure differential. In a straight finite wing, the air is free to flow from the high pressure region under the wing to the low pressure region above the wing, ultimately flowing up and around the wingtip, which induces opposing spanwise flows on the upper and lower surfaces of the wing. At the end of a wing, the airflow is almost circular due to the pressure differential generated in a lifting condition. On the underside of the wing, the flow has a spanwise component moving outboard, and on the upper surface of the wing, the flow has a spanwise component moving inboard. So a portion of the total airflow in the region tends to travel outboard along the span, up and around the wingtip, and inboard once we're on the upper surface. It's also worth noting that the magnitude of these wing-induced velocities generally increase as we move outboard towards the wingtip. Anywhere along the span of this wing, these induced velocities will usually be highest just outside of the boundary layer, so relatively close to the wing surface itself. The pressure differential and spanwise flow generate vorticity along the entire span of the wing, which ultimately concentrates at the wingtip into two strong and well-known vortex structures referred to as wingtip vortices. You can sometimes see these vortex lines form on plane wingtips when flying in a region of high humidity. What's most important to understand is that the wingtip vortex produces a downwash of air behind the wing, which is the strongest at the wingtip, and then decreases in strength as we move inboards towards the wing root. So if you don't know what downwash is just a result of the air being deflected downwards by the wing. Think lift generation due to Newton's third law, right? You push the air down and your aircraft goes up. The wingtip vortices are not what causes downwash, but occur just as a result of the downwash. So even an infinite span wing would generate downwash still, but would be absent of any wingtip vorticity. Clearly, if air around a wing is downwashed or given some downwards velocity component, the effective angle of attack, especially near the wingtip, is decreased. This means that an additional downstream component to the resultant aerodynamic force acting over the wing, especially near the winglet, is introduced. This downwash-induced downstream component contributing to the drag is called induced drag because it has been quote-unquote induced by the action of the wingtip vortices. This local drop in effective angle of attack near the wingtip due to the wingtip vortex also decreases the overall lift of the wing, which is another reason why we want to minimize the effect of the circulation gathering around the wingtip as a result of lift generation. It's also worth noting that there are more complete explanations here, which involve circulation in what's called vortex sheets extending from the trailing edge and running the entire span of the wing. But I really think that concepts like free and bound vortices and a few other concepts are out of the scope of a quick and digestible understanding like we're getting in this video. Wingtip vortices are really just the beginning of a whole vortex picture, because this is the first place that it really has a chance to occur. To summarize, induced drag is not actually created by the wingtip vortices. The wingtip vortices are just really a manifestation of the overall span-wise flow effects and vorticity across the span generated as a result of generating lift itself. Now, this also affects the lift distribution over the entire wing because the wingtip lift has to be resolved to the free stream reference lift or 0. For more on why this affects lift and not only just drag, see the first video in this series, which dedicates several minutes to lift distributions. Just for reference, I've included the equation describing this effect. You can see that the final lift coefficient is equal to the free stream ideal lift coefficient divided by a quantity that basically just means that the lift increases with aspect ratio. A classical representation of the induced drag phenomenon is called the horseshoe vortex system. Now remember that nothing is free in flight and that by producing lift we must pay a price. So our job as engineers is to get creative and find some way to minimize this energy loss, because losing energy by imposing any unnecessary motion in the air that we're moving through, which in this case would be a vortex structure as a consequence of lift, is a huge waste. First, let's quantify induced drag so that we can properly investigate which parameter should be hunted down and either increased or decreased until our induced drag hits our target decrease. In one of my last videos, I quickly glossed over the topic and accidentally incorrectly stated that the induced drag increases with velocity, so here's why that's incorrect. If we're generating the same lift, so that would be a condition of maintained altitude flight, and increasing airspeed, CL will be decreasing with the increase in Q. If a plane or a lifting body increases speed while holding a constant altitude, the only way for the lift to stay constant and not increase in altitude would be if alpha decreased, which is just decreasing CL. Since the induced drag coefficient is proportional to the square of CL, it's clear that the induced drag decreases with the square of the velocity increase. It also depends on the square of the weight of the aircraft divided by the square of the span length. The equation defining these relationships shows us that the induced drag increases with the square of the weight of the aircraft, or the lift required, and decreases with the square of the span. I've also reviewed the wing efficiency factor in the first video in the series. What's important to know here is if we purely want to maximize this efficiency factor and decrease induced drag, elliptical wing loading, where the lift force is the greatest at the root and decreases towards the tip in a manner that follows the equation of an ellipse, should be sought after. So back to our big question, how can we minimize the energy lost to overcoming induced drag? Or in other words, how can we minimize the amount of energy lost to the rolling up of the wingtip vortices generated by the span-wise flows induced by producing the necessary downwash for our flight condition? It should be obvious that maximizing the aspect ratio of a wing will minimize the induced drag generated. With the higher aspect ratio wings, the lift distribution becomes more efficient across the span of the wing, and the wing generates less intense wingtip vortices because there's less span-wise flow towards the tips, leading to weaker vortices and therefore reduced downwash. So the higher the aspect ratio, the closer to quote-unquote infinite span a wing becomes, and as an infinite span wing will naturally have no span-wise flow induced by pressure differentials, the closer we get to infinite span, the smaller our span-wise flows get, and therefore the smaller our induced drag gets. In simpler terms, as a span approaches infinity, the induced drag approaches 0. We can instead try to emulate the infinite span wing by using end plates that extend far from the airfoil section. Naturally, no span-wise flow would occur here as there's no freedom for the air to travel from regions from high pressure to low pressure. Now, obviously, to be effective at reducing the span-wise flow and induced drag with an end plate, the end plate has to be so large that the increment of skin friction drag due to the extreme wetted area would outweigh any reduction in induced drag. So this is where this video comes in. Winglets offer a more effective solution to this delicate balancing act. One of the earliest solutions to decrease induced drag, besides increasing the aspect ratio of the wing that is, was what's called a winglet. So what winglets do is alter the span-wise distribution of circulation along the span of the wing, and naturally this alters the structure of the trailing vortex system downstream. The induced drag reduction due to the addition of a winglet is a relatively trivial calculation, and it's easily verified with the vortex lattice analysis. However, it's easier for some to consider the flow field itself rather than just the numbers in which the winglet is inserted into when added to an existing wing. Unlike a simple end plate or fence, a winglet carries an aerodynamic load. Its purpose is to create a flow field that interacts with the main wing's flow field in a manner that decreases the wing's overall span-wise flow. Essentially, the span-wise induced velocities from the winglet itself counteract and cancel those produced by the main wing if the winglet is designed properly. Now, this is an elegant solution that cleverly uses aerodynamic loading to accomplish the same reduction in main wing spanwise flow by using significantly less wetted area than the equivalent flat and excessive end plate. Remember that the profile drag increases with velocity while the induced drag decreases, so this is where good engineering judgment and analysis is needed to determine the optimal operating window for winglet design. Proper optimization will result in the greatest reduction in induced drag for the smallest increase in profile drag. This optimal point can be considered a crossover point, and below this crossover point, below this airspeed, the winglets provide a performance advantage, but above this crossover point, above this airspeed, the additional wetted area generates enough profile drag to decrease the overall performance and overall outweigh the advantages that you gain with the winglet. So this is all great information, but how can we use it to our advantage? Before jumping into design principles and guidelines, let's keep digging just a little bit further into the theory behind how winglet aerodynamic loading can decrease the induced drag. If we change our reference and look at the cross-section of the winglet instead of the cross-section of the wing, so now we're looking presumably orthogonal to the wing, if we add the spanwise velocity induced by the wing as a vector component to the free stream velocity vector at the wingtip, you can see that any vertical protrusion at the wingtip will experience an effective angle of attack, which will generate a lift force tilted forwards. This net force can be generated by a winglet above or below the wing. If the vertical surface is extending downwards, the resultant lifting vector of the winglet points outboard due to the local induced velocity, but it's still ultimately tilted forwards. Naturally, to maximize this effect, we should be using cambered airfoils that will be effectively lifting inwards towards the wing root. Some people just assume that a symmetric airfoil cross-section of winglet is okay, but this is just lazy, and you're leaving gains out to save a few minutes of preliminary analysis and calculation. I won't dive into the derivation of this equation because it's actually simpler than you think, and the McCormick Aero book is a phenomenal read. I'd actually recommend you to not just trust some random dude on YouTube showing you an equation, but actually go and spend some time and understand the derivation of the equation for yourself. Anyways, this drag coefficient relationship indicates that with winglets, the CD reduction increases linearly with the square of the lift coefficient. This should sound familiar because we reviewed a simplified form of this equation a few minutes ago. Also, it's important to note that with this relationship, at low lift coefficients, the drag coefficient will be increased with winglets. Remember what we reviewed earlier. The drag coefficient isn't just induced drag, there's also several other factors contributing to this. Again, this makes sense if we take a second to think about it. Induced drag is the penalty for generating lift. If we're generating only a little bit of lift, or we're at a low CL, of course the increase in profile drag and skin friction due to the addition of a winglet will shadow the decrease in induced drag. Remember also that high winglet aspect ratio is desirable. Cool, now we understand what this equation means and its general effects. Now, what design tips can we take from this equation? While winglets are used to improve aerodynamic efficiency by reducing induced drag, they also add their own sources of drag. Therefore, the profile drag of the winglet and the interference with the main wing must be minimized. It follows that a high aspect ratio winglet is preferable, and this will generate a steeper CL alpha curve and a lower induced drag generated by the winglet itself, because after all, this is just a smaller wing at an effective angle of attack. It's just oriented vertically instead of horizontally like a main wing. I also mentioned a minute ago that the magnitude of the wing-induced spanwise velocities generally increase as we move outboards towards the wingtip. This means that to have the most effective winglet, it should be placed where the induced velocities are the highest, which is at the very end of the wing, of course, to increase the effective angle of attack on the winglet, and therefore increase the forward-oriented resultant, quote-unquote, thrust vector. Now, as any good engineer will always point us back towards the pay-to-play nature of aerodynamics and aeronautics, think, what are the consequences of a proper wing design that either decrease induced drag by increasing the main wing aspect ratio, or alternatively by just the addition of proper winglets? Okay, let's say we designed a perfect winglet for our design flight conditions and we've minimized the weight addition due to the increased wing root structural demands. Why don't we see winglets everywhere then? If engineers can dedicate time to generate the perfectly optimized winglet, why aren't there winglets on every plane? Winglets aren't a perfect solution, and they can cause issues if they aren't designed with a lot of care and precision to overcome the adverse effect of the added weight, complexity, part count, and profile drag. You'll hear a lot that because wingtips add weight and generate a maximal bending moment at the root for any given weight, since they're the farthest you can possibly get from the root, that the wing structure has to increase in weight to accommodate for the loading increment due to the addition of a winglet. However, let's think through this together for a second. In a lifting condition, the lift bends the wing upwards, and the weight of the winglets will effectively counteract a portion of this bending load on the wing root. Also, if you get creative and design the winglets so they generate a load that points outward, then you can slightly decrease the wing root bending moment further and kind of bend the wing back down from its bent up lifting state. Obviously, if we can save some weight now on the wing structure, we can get further gains in aircraft efficiency by saving weight. However, if the aircraft in question is already small and must take off from short runways, then the weight addition in the non-lifting condition or during takeoff while still on the ground will be a bad thing, as the minimum distance for takeoff will be increased because the aircraft has to accelerate more weight to a faster takeoff speed that generates more lift. You may have noticed that a lot of the larger planes like commercial airliners have winglets, but smaller planes tend not to have winglets. Why is this? It's actually pretty simple. So remember that wingtips are here to increase the effective wingspan, but they still generate form drag and add weight. On most small aircraft, the perspective improvements in efficiency don't really ever exceed the weight and form drag increment that result from adding the winglet. You will, though, see that there are sometimes these small morphed wingtips called Horner winglets on smaller aircraft. This gives aerodynamic benefits of wingtips at lower airspeeds, but really minimize the additional form drag and add virtually no weight. So let's go one question deeper. If Horner winglets offer similar benefits to traditional winglets, again without the drag and weight penalty, then why aren't they used on the larger aircraft? In simpler terms, at higher airspeeds on larger and more swept back wings, the spanwise velocities on the wing will be comparatively stronger and will, at some crossing point, see the Horner wingtip no differently than a plain rounded wingtip. At this crossing point, the larger full winglet will be necessary for any further span-restricted efficiency gains at high lift coefficients. It's also worth noting that the weight fraction of a winglet on a commercial airliner is much lower than that of a small aircraft, and adding a winglet to the lower aspect ratio minimally swept wing that you would see traditionally on a small aircraft would meaningfully decrease any payload capacity at the expense of a likely negative efficiency increase. Often, aircraft will have wingspan limitations to fit into certain areas in an airport, such as specific taxiways or into specific terminals. There's also a thing called an aircraft design group in which different aircraft pay different amounts in airports depending on how large they are, and bumping up into larger groups increases costs everywhere. A winglet has the advantage of not increasing wingspan, but increasing the effective aspect ratio by increasing the effective wingspan. A creative solution to this is the hinged rake winglet, which folds up upon landing to prevent commercial aircraft from bumping up into higher and more expensive design groups. All of this is super good to know for conventional aircraft, but you guys know me, big flying wing guy. So are any of these any use on flying wings? We've learned that flying wings utilize the bell-shaped lift distributions and kick the wingtip vortex inboard of the wingtip, and therefore generate upwash near the wingtips. So would a winglet even be effective? MH Aero Tools ran a cool little study on 4 different winglet configurations to demonstrate how careful we really should be when throwing a winglet onto a flying wing specifically. Here you can see that we're comparing 3 winglets to a plain wingtip on the same wing. The boundary layer on the suction side of the wing is already super sensitive to the pressure rise, which occurs beyond the point of maximum thickness in the airfoil. And the quicker the pressure rises here, the earlier the boundary layer will transition from laminar to turbulent, or it could even potentially separate from the airfoil surface, which would obviously increase the drag here significantly. Knowing this, you can see how a winglet, specifically a winglet with a sharp transition to the wing, could be an issue. Usually the wing airfoil only feels the pressure rise on the suction side in just one dimension, but with an effective winglet, another new spanwise pressure rise gets added to this in the winglet corner. The boundary layer pressure field in the region will have to overcome the sum of these 2 pressure rises, which naturally gives a higher risk of boundary layer separation. And we can minimize this effect by just blending the winglet into the wing with a wide, large radius blend to avoid a sharp corner. We can also kind of decouple the pressurized regions of both airfoils here by simply shifting the winglet downstream. This just moves the wing's pressurized region closer to the winglet's pressure drop region towards the leading edge, and this partially cancels out the wing pressure rise, which leaves us with a slightly more favorable flow field in the wingtip region than if we had no winglet there in the first place. Moving the winglet downstream for low Reynolds number applications like UAVs or MAVs will just induce a larger region of laminar flow near the winglet. The result of adding a winglet will be just better than a wash on the overall non-lift induced drag. What we're talking about here is a slight decrease in form drag, but we're still ultimately increasing the wetted area of the aircraft by the addition of the winglet. The results of this study would indicate that a blended winglet shifted slightly downstream will perform best, but only by a small margin. As would agree with the relationship between induced drag and lift coefficient that we looked at earlier, any winglet becomes very effective in decreasing drag at high CLs. We can use a winglet that extends straight up from the wing with no issues, but we can also shift the leading edge of the winglet back as if the winglet had some sweep to clean up the velocity distribution near the wingtip and overall maintain a clean and minimum local pressure rise on the adverse side of the airfoil out towards the wingtip. So far we discussed the boundary layer effects of the study and the friction drag associated with the winglet addition, but let's not stray from what winglets intend to do, and that is decrease the induced drag. We can discuss the boundary layer effects and the pressure distributions all that we want, but they wouldn't really be useful if the different winglet configurations here showed majorly different induced drag results. Remember again that we love tailless aircraft here, at least in this series, so while the intent behind winglets is traditionally to reduce induced drag and the downwash delta due to the spanwise flows, we can use winglets as a different tool for planes with no tails and can use them to drastically increase our directional stability while still realizing some of the induced drag reduction benefits. If we use winglets on a flying wing, then there's not really a point of using a vertical fin like you'd see in a conventional aircraft. The delta in skin friction drag between a tail, including the supporting empennage, and winglets can still be worth the jump from tail to tailless aircraft, even if we aren't shooting to decrease the induced drag. Talking about increasing directional stability now, remember that from the last couple of videos, we can achieve sufficient directional stability through a combination of sweep, taper, and nonlinear twist in a flying wing, but even then the stability can still be low and challenging. Winglets here can provide a healthy increase to the stability and can also provide some slight efficiency increases, if any. Moving on to practical design, how should we approach the design of a winglet? First, let's review common winglet nomenclature. Toe refers to the angle between the winglet and the wing's chord plane when viewed from above in a plan view. Toe indicates the horizontal rotation of the winglet's base relative to the wing's direction. Adjusting the toe angle can optimize the aerodynamic interaction between the winglet and the wing, which in turn can reduce the downwash over the wing generated by the wingtip vortex. If we carefully optimize the winglet airfoil's angle of attack relative to the local flow around the wingtip, we can squeeze more induced drag decreases out of the winglet. We can do this by adding slight toe in to an upturned winglet or slight toe out to a downturned winglet, which in both cases will increase the winglet lift generated by geometrically increasing the alpha experienced by the winglet. Again, this resultant vector is tilted forward and reduces drag by providing thrust through the winglet loading, but we still have to be careful not to get near winglet flow separation conditions and stall anything at any point in our flight envelope. This is all information about efficiency manipulation, but winglet toe angle plays a pretty big role in the directional stability of tailless aircraft. If the winglet is towed in, the drag of the advancing winglet during the yawing motion will be greater than that of the retreating winglet, and this induces a restorative weather vane motion. On the other hand, if the winglet is towed out, we get the same effect, but now the restorative force is the winglet lift instead of the drag. A lot of times, the lift is more difficult to accurately predict, so it's often easier to rely instead on the drag force and the toe-in winglet condition for directional stability. As a quick sidestep from the winglet geometric properties that we are reviewing right now, there's a cool little trick with wingtip sections where we can obtain directional stability on a swept wing through negative dihedral, which is anhedral, and twist. Simply put, the wingtip is bent downwards and at the same time tilted forwards. Now this definitely doesn't have to be across the whole span, and we should really be careful not to induce rolling instability with any anhedral. If you have any questions on what affects yawing and rolling stability, see my last video about aerodynamic stability. Anyways, if we design the wingtips with a bit of anhedral and washout, we can simulate lower surface wingtip fins or winglets, and the directional stability will then be manifested through the outward lifts generated by the wingtips. You'll probably only ever see these on flying wings. If diffuser tips are used, we can pretty easily increase directional stability, and this helps make up for the absence of the vertical tail in the tailless aircraft. The drag that these produce also acts in a similar manner to the toe-in winglets. Just remember that when considering diffuser tips, they do generate slight downward lift. Since these can replace fins and rudders and potentially some wing twist if designed correctly, then the lift deficiency caused by the diffuser tip can be tolerated. Alright, back to the traditional winglet geometry. The winglet twist is just like wing twist and describes the variation of the angle of attack along the span of the winglet. This can also be played with to improve the wing's lift distribution by reducing the strength of the vortices again. Sweep in a winglet is measured just like wing sweep and has similar effects. At higher speeds, just like wing sweep does, winglet sweep can reduce wave drag. Unique to winglets, however, is the cant angle. The cant angle describes the inclination of the winglet relative to the vertical plane when viewed from the front. This describes how much the winglet is tilted outwards or inwards from the wingtip. Positive cant angle, or a wingtip that is tilted away from the fuselage, is the most common winglet orientation and can help redirect the wingtip vortex flow away from the main wing's wake. Some of the most common types of winglets that you'll see on various aircraft include blended winglets, tip fences, raked winglets, upswept and downswept winglets, and Horner winglets. And then sometimes on more unconventional aircraft and experimental research, you'll see spiroid winglets and wing grids. Each of these have their own pros and cons, and each are chosen and designed for a specific flow field and specific pressure distribution in the wing into which they're incorporated. I'm sure someone's asking at this point, why are all these winglets bent upward? I've asked the same exact question, just trying to challenge the norm and really to understand why they're mostly bent up today. Aside from the obvious concerns like ground clearance, is there a reason that an upturned or a downturned winglet would be more effective than the other? Ignoring one of the greatest aircraft of all time, the XB-70 Valkyrie, which used downturned winglets for compression lift, let's just think about the difference between upturned versus downturned winglets from a flight characteristic standpoint. For efficiency, the winglet orientation doesn't matter too much, but it does for maneuvering and handling. Think about the upturned winglet during a turn involving a roll. As the left wing rolls right, the left wing will generate more lift, and the winglet inherits some of the wing's increased lift. I won't go into too much detail about that, I'll leave that one for homework. This means that the left winglet's inward porting force increases, and since winglets are usually on wings with some sweep and aft of the CG, this inward side force will now yaw the aircraft left away from the roll, which is normally what we refer to as adverse yaw. Now, alternatively, consider a downturned winglet. As we learned a few minutes ago, the downturned winglet will generate a force pointing outwards, so when the aircraft rolls to the right, and the left wing generates more lift than the right, and the left winglet again inherits some of the wing's increased lift, this outwards pointing side force produced by the winglet increases. Since this is behind the CG, this will yaw the aircraft to the right and into the turn. In a similar manner, in a side wind condition for an upturned winglet, say blowing from the left to the right, the upturned winglet will have the aircraft roll rightwards or away from the wind and yaw to the left or into the wind. Alternatively, for the downturned winglet, the same wind will cause the winglet to roll the aircraft left or into the wind and also yaw left or into the wind. So this is great for static stability. It's pretty cool stuff, even if downturned winglets are impractical sometimes just due to non-aerodynamic constraints. Alright, let's say we're looking to increase efficiency for a conventional or tailed aircraft, and the addition of a winglet crosses our mind. Obviously, our first question to ourselves should be, do I even need a winglet to increase efficiency? Obviously, we're looking to increase efficiency, that's why the winglet would cross our mind in the first place, but can we do this with a span increase? Increasing the span, and therefore increasing the aspect ratio, will always be more efficient than that of an equal length winglet addition because of several reasons. First of all, the span increase or wing extension and winglet would have about the same viscous drag at low angles of attack in most cases, and both can increase maximum lift and both can lower induced drag, but a wing extension will create the most lift for a given wetted area increase, and the wing extension is more than twice as effective in lowering the induced drag. At non-optimal and non-cruising AOAs, the wing extension will give a better circulation distribution along the span. However, the wing extension will produce the highest root bending moment for a given amount of lift. Consider the hypothetical that a winglet is just as good as decreasing the induced drag as a wing extension, which is obviously not the reality. The reason that the wing extension would still be the preferred method to increase the efficiency is that the wing extension still generates a higher L over D due to the extension generating additional lift in the wing versus the winglet generating a side force. We've covered a lot of material and theory in the last half hour, so let's sum it up. The total drag on a lifting body in an incompressible flow is classified into two groups, that's viscous or profile drag and induced drag. Induced drag is the consequence of generating lift and is not actually created by wingtip vortices. The wingtip vortices are just a manifestation of the overall span-wise flow effects and vorticity generated as a result of generating lift. Induced drag is just the backwards pointing part of the pressure force vector. Wherever possible, if we're seeking efficiency gains, we should first increase the wingspan with a wing extension. When we're span limited or wing root bending moment limited, winglets are a great alternative to the wing extension for increasing efficiency at high lift coefficients by reducing the induced drag. On that note, winglets will never decrease induced drag as effectively as just increasing the span using the same length used for the winglet, and the winglet will always give lower efficiency increases than the wing extension will give. Compared with the wingspan extension, winglets usually produce lower additional bending moments in the wing spar, which make them useful for retrofitting existing wings without increasing the structural mass of the existing basic wing. Winglets should be carefully designed and analyzed for the unique flow field that they're manipulating. Geometric properties such as cant, twist, toe, sweep, and aspect ratio are all important to optimize considering the additional aerodynamic loading generated, supporting structure weight required, and efficiency gains. On a flying wing, winglets may benefit the directional stability greater than the efficiency. This all depends on the span-wise lift distribution, and if the wing utilizes an upwashing wingtip section, like that of a bell-shaped distribution. Pivoting to the good practices of traditional winglet design processes, the winglet airfoil should, in most cases, be cambered, and if the winglet extends above the wing, the cambered airfoil should be lifting inwards, and if this airfoil is also towed inward geometrically, then you further increase the induced thrust vector and decrease the induced drag. That toe-in will also provide directional stability through winglet drag. If the winglet instead extends below the wing, so extending down instead of up, that same cambered winglet airfoil should be pointing outwards now. And if you tow that winglet outwards and you get geometric toe out there, you can increase the induced thrust vector, again decreasing induced drag. And that toe out will also provide directional stability through the winglet lift instead of the drag. For various reasons that we discussed in this video, the winglet should probably be swept back a bit. Using a cant angle in the winglet, that being the winglet sitting somewhere between 0 and 90 degrees canted off the main wing, can prove beneficial at certain Reynolds numbers on certain wings, but the exact angle should really be optimized for extensively if any cant is present in the winglet at all. Everything considered, if you made it this far in the video, I'm sure that you're already smart enough to know that these are all design principles for the early decision stages, the early concept stages, the early design stages, and the detailed design of a winglet should really be driven by data. This could be data anywhere from preliminary CFD data to detailed wind tunnel data. And all this data of your wing and wingtip region, you should be able to balance against the structural requirements and the mass properties of your aircraft. Anyways, we could talk for days about winglet design and some of the cooler unorthodox winglets that are being researched right now, but I'm going to leave some of the research up to you, and as always, I encourage you to read these books and papers for yourself to increase your understanding of aerodynamics in general. Thanks for watching.